Be a recap of the demonstrations that we've been doing, and we're going to formalize the concepts that we were, that were in the background that we didn't make explicit. We're going to make those explicit now. So again, formally, an object is characterized is an entity, a general entity characterized by three things: identity, state, and behavior. Right? This goes. The second two go into encapsulation. Encapsulation is the grouping of data together into one logical unit, the protection of that data from the outside world, and then the grouping of functionality that acts on that data, just like we did in the book class, the author class, the isotope class. Right? An identity, however, is an aspect of the object that distinguishes it from all other instances. For example, if you remember back to the book class, right, we were trying to find all the books by Frank Herbert. But initially, in our first design, we also got his son's book, Brian Herbert's book, right? How did we distinguish between those two authors? We went up to Eclipse and we had it generate that equals in that hash code method. So in Java, all right, let me go ahead and add this at the front. In Java, identity is implemented using the equals and hash code methods. Right? There we go. Now, the way that Eclipse did that is that it gave us an option that you want to identify this object based on the first name, the last name. Right here it is. In fact, here's the person class: first name, last name, and date of birth. Here's our equals and hash code method. You could, of course, go ahead and, excuse me, I think we added the date of birth later on. And so this is just based on the first name and the last name. And it auto-generated this code for us. That's what identifies a person from another person, so that Frank and his son, Brian, are now different people. What if this were coming from somewhere else? What if it were coming, say, from a database? Or something where we've got a unique identifier. Or in the case of a person, what if we had a string social security number, right? That would probably end up being our unique identity, right? So I'm going to go ahead and get rid of that though, but you get the idea, okay? The state is the collection of properties. We sometimes call these elements, attributes, data, fields. But what we're going to do is we're going to call them member variables in the context of Java, right? That simply means that you're taking all of those elements that make up that object and you're putting them into one class. You're collecting them together. And then finally, the behavior, the functionality that acts on that data. For example, in the isotope class, right? We had this functionality called decay. You give me a duration, and now I'm the isotope class. I've got a certain amount of mass, right? The 10 kilograms or whatever. You give me a duration, and I'll go ahead and decay myself according to my half-life, my current mass, and the duration that you give me, right? I am using my properties, my member variables, to compute that. It would not be appropriate, it would not be good design to locate this function outside the class, somewhere completely different. That would be breaking encapsulation and breaking this third aspect of what objects are. I will say right now that Java is a class-based object-oriented programming language, like we've emphasized before. There are object-oriented programming languages out there that are not class-based. They're few and far between. The primary example would be JavaScript. JavaScript has object-oriented programming, but it does so in a prototype. It's prototype-based. The original versions of JavaScript did not have classes. Guess what? Subsequent versions did add classes. Why? Because it's the easiest, most clear way of doing things. So the vast majority of object-oriented programming languages do have classes for you to define, just like Java. Right? It's not the only way, but it seems like it's the common way of doing things. Okay? Otherwise, communication between objects is done via what's called message sending. Right? I don't decay that isotope. What I do is I send a message to that isotope to say, decay yourself by a certain duration. That's what we mean by method sending. Yes, at the end of the day, I'm invoking a method, and that method is running some code. But from a philosophical point of view, from a programming language paradigm point of view, I am sending a message off to this object so that it can act independently. Right? that it is abstract, all that stuff is abstracted away from my understanding. Communication is facilitated by an object's interface, the public methods that are available to it. All of these methods were public over here in the isotope class. But what if I had another method over here called, I made it private, do something else, right? There we go. Private, and we'll make it a void function so it doesn't actually do anything. Maybe it just prints out a message or something, right? Now, am I going to be able to see this from my demonstration class over here? Right. Here we go. There's Strontium. Let me go ahead and see if I can invoke that method on Strontium. Strontium dot do something. Right. Am I going to be able to send a message to that Strontium sample to do that something, whatever it is? No, because it's private. The method to do something is undefined for the type isotope. It's not even telling me that it exists, right? It's completely hidden from the outside world because it is not part of the publicly facing interface of that object, okay? What you observed, I guess, Wednesday in your labs was that objects are constructed rather than just assigned. In a programming language, if I've got like a primitive type like an integer, and I say int a is equal to 42, right? 42 is not even something that a computer understands. The compiler takes that 42, and because that integer is built in, it changes it into this 32-bit binary value that it loads up into a register, into a memory location, and it takes care of all those details for you because it's built into the language. Likewise, small d doubles, strings, right? Those are all taken care of by Java. Right? What's not taken care of by Java is when you do your own user-defined type, like an isotope. At that point, yes, if you don't provide one, one will be provided for you. I'm talking about a constructor here, a default no-argument constructor, because it needs it. It's automatically built into the language. But if you want to specify different behavior, for example, setting the atomic number, setting the element name, right? Allowing the mass to be null, right? That is your responsibility. And you do so by creating a constructor. By default, a no-argument constructor is provided for you. If you define your own constructor, it goes away, just like you saw in your lab. And then you can always restore it if you want to by simply explicitly defining it. You can define as many constructors as you want, right? Again, it's a gift that you give to yourself. I need a way of creating this thing with just these 3 things over here instead of those 4 things over there. Then do it. Right? Just create another constructor. You don't even have to type any code, right? Because all you have to do is go up to source, generate constructor using fields, click, 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 you're done. Okay? There are some common patterns that we covered. For example, copy constructors that take an instance of an object and make a deep copy of that object. This is particularly useful for built-in types like lists. If I have list A and I want a copy of it, list B, if I just say that B is equal to A, that's what's called a shallow copy. I've got these 2 references that point to the same thing. So that changes to one will affect the other because there's really only one list there. But I can use a copy constructor and say that I want this brand new list to be a complete deep copy of that list over there. I go ahead and give it to the constructor and it'll copy everything over for me automatically. We also had partial copy constructors, in which I did want to create a copy of an isotope so that I didn't have to repeat myself, 38 strontium 90 SR 28.9, right? And I just passed that off, but I did want a different mass. I wanted 10 kilograms here, 5 kilograms here. Right? That's going to be a very convenient pattern for you to use, especially in your projects. Right? There's objects design that we basically covered implicitly. How did I know what an isotope was? Well, the exercise told me, right? There are these 5 pieces of data. How do you know what a weather data is? What is weather data from your first assignment? It's a date and a temperature, right? What is that? Again, screaming out to you? Make a class. Do you really even have to think about it? No, it's completely specified. That's what we mean when semantics dictate design. Right? If you just start thinking about what is a person, well, a person has a first name or a last name, probably should separate those, right? And also they have a date of birth, and also maybe they also have a bunch of emails, right? Private. We'll just go ahead and go with a list of strings to indicate their emails, right? There we go. Now I'm going to have to bring this in as an import it. There we go. And I'm going to also have to make sure that that's initialized. This.emails is equal to new array list of strings. And I can explicitly say string here, but it's not necessary with modern Java. Right? You can elide that away. There's your 50-cent word for the day. Elision. Anybody know what elision is? So in speech, when you take out syllables to make it quicker, right? So you're gonna do your design document today, right? You're gonna turn it in. What did I do? Are you going to, right? But I didn't say going to. What did I do? I elided away a few syllables because of my speech pattern. Gonna. Are you gonna do that, right? That's what elision is. So I don't have to explicitly state that this is an array list of strings. Instead, all I have to do is say, well, you figure it out, compiler. Oh, compiler says, okay, it's a list of strings. I figured that out for you. Right? That's what's called elision, right? You're eliding it away. Right? Let's see. Well, I don't have a constructor here that allows me to give it emails. One thing I could do, of course, is change this constructor so that I do have a list of strings emails, right? Although I want to go ahead and follow a different pattern here. Maybe later on, because they might have more emails later on, maybe I'll go ahead and allow you to add an email. Public void add email, and then string email. This dot list of emails dot add email. That's going to be really, really convenient because now up here in the constructor, I don't have to give you a bunch of emails that have already been pre-computed. Instead, I could say, well, here's a person, here's their first name and last name. Oh, and also, they have a Huskers email. There you go. They have a UNL email. There you go. They have a Gmail account. There you go. Right? So that's when redesigning this just a little bit allows me a little bit more flexibility. Right? But again, it all goes back to semantics dictate design. What is that thing that you are modeling? Right? And if you just start answering those questions, or if it's really, really well specified already, it should be pretty straightforward. Don't over-design, though, right? Remember that Yagni principle? In the isotope class, we decided, well, no, we'll just go ahead and keep mass as a double. We don't need a class to represent mass with some universal kilograms, and then you can go ahead and mix in pounds and grams and whatever, right? Why? Yagni, you ain't going to need it. Right? Don't over-complicate things, right? If eventually you do have a very good reason to implement a mass class, then go ahead and do so. Right? But you don't have a good reason yet. We did have a good reason to implement or require a duration because when I looked at that one, I didn't know if that was a year, a second, a day, whatever. Right? So we made this universal, but it was already built into the language, so we just used it. Right? So I had a somewhat good reason, but also I had another very good reason that it was already done for me, so just use it. You break real-world objects or ideas into smaller and smaller parts until either A, it is directly representable, that thing is a string, that thing is a number, that's built into the language, or an object already exists for it. That thing is a date, local date, good to go. Don't make your own date class. Duration, we're good to go. Let's use that because it's already built into the language. Right? Generally, your objects are composed of other objects or data. For example, over here in the person class. Right? The person class is actually a first name and a last name, but what is string? It's a class. Right? There it is. Right? It was just built into the language. It's composed of two other classes. In fact, here's another class, local date. What is that? That's another class. What is list? Technically, that's an interface, but an array list is another class. Right? Classes are composed of classes are composed of classes. That's the pattern you should be following. Now, I do mention that it's called composition because one thing is composed of other things. That's where the story stops with a language like Java. All right? With a language like Java, an object owns an instance of another object. It's called composition. If you are going to be doing any like C++ programming, there is a far deeper nuance to composition because there's ownership, there's an association, and there's I forget the third word, but there are levels of composition. Basically, it all boils down to, well, what happens when I delete this person, right? Do I also have to delete this string? Do I also have to delete this other class over here? In a programming language like Java, that's completely irrelevant, because do you need to clean up memory in Java? No, it's auto garbage collection. But in a programming language like, say, C or C++, then it becomes important. Because if you're going to clean up an array, what else do you need to clean up? Everything inside that array, and everything that that array refers to. Right? Those are called destructors, right? In C, or cleanup functions. They're called destructors in destructors in C++. We don't really have objects in C, but you do have the same idea. Right? If you need to clean up memory, then there's a whole bunch of other things that go on with composition. Avoid the God anti-pattern. One of the common problems that we saw in, say, assignment 1 is you put everything into main, say, for the weather data, right? That means that we had a main that was somewhat like 50 lines of code. Shouldn't have been that way, right? Each one of those reports should have been screaming out to you, put that into another function, put that into another function, put that into another function. Call that function, call that function, call that function, right? You can do the same thing with classes. Avoid the God anti-pattern. A class should only know about its own stuff. It should not know about everything, do everything, and be everything, right? That's what God is, right? You don't want a God anti-pattern. An anti-pattern, by the way, is a bad habit to get in. We won't explicitly talk about what patterns are, but patterns are good habits in object-oriented programming. They're common, repeatable patterns that you can follow for good, maintainable code. An anti-pattern is just the opposite, a bad habit to get into. So, for example, when I started out that book class, way up here, let's close that. That book class, we started out with representing an author as a first name and a last name. Guess what? That means that the book class knew about author stuff as well. It was becoming slowly, and if we kept doing that, it would have become the God class. If instead it was a first name and last name, first name, last name, and also we do want the release date, so maybe that's going to be a year, a day, and a month, right? Now the book class knows even more stuff. It knows about author stuff. It knows about date stuff. It knows about book stuff, right? Now it's God. It knows everything. It does everything, right? We don't want that, right? We want to put person stuff into the person class. We want to put date stuff into the date class, and only book stuff belongs in the book class. Otherwise, it's a God anti-pattern, okay? That was kind of a review of what we did over the last week or week and a half or whatever it was. Now we're going to get into more of the actual pillars. We call them 4 pillars. There's a 5th pillar, objects, which is what we were talking about the entire time, right? But have you ever heard of a building with 5 pillars? No? Okay. I'll tell you a story. Since he's retiring, it doesn't really matter. I won't name names, but they had a vision for the university with these 4 pillars, right? And like agriculture, something, and then somebody pointed out, you know, it's the 21st century. Maybe computing should be one of those pillars. Oh, there are 5 pillars right now. And so magically now we have a building with 5 pillars. Like, I don't know, it's in the middle of the building or something like that. No building has 4 pillars, or 5 pillars. They only have 4 pillars that are holding up the building, and one at each corner. And in object-oriented programming, we've got abstraction, encapsulation, inheritance, and polymorphism. These two, abstraction and encapsulation, basically are what we've been talking about for the last 2 weeks, right? Just not calling them necessarily those things. What is abstraction? Well, it's information hiding. How is something represented, right? You should not have to worry about the details of an object and how it's represented just to be able to use it, right? You just use its interface. So for example, let's come over here to the demo. And let me start out with something that is very familiar to everybody here. Math.square root. Right? Square root of 2. Right? Double y is equal to. Did you have to think about how the square root thing worked? No, why? That's procedural abstraction. In other words, whatever steps it takes to execute and to compute the square root of 2, right? That's hidden away inside this function. Have you ever been curious to find out how it works? Let's find out. There we go. Okay, well, it calls this other function called strict math. Let's go ahead and check that out. Uh-oh. Do you see any code there? No, why? It's calling C, all right? The C programming language's math library. Python does the same thing. If you just look at the source code for Python, what is it doing? It's calling C. Java here is calling, it's called a native, right? It doesn't necessarily have to call C, but that's what it is, right? Nobody's ever, once C wrote the square root function, nobody ever had to rewrite it in any other language. Instead, you just write your language to call the C function, right? All right, so did you have to worry about any of that? There's some interpolation method. There's some Taylor series or something hiding under the hood. Who cares, right? That's the answer that you should have, right? Who cares? Likewise, data representation. How does local date actually represented? Well, first of all, what's the answer? Who cares, right? If you really want to find out, though, where is it? Let's go into person, local date, right? All right, we'll take a look at this in a second, but there are several options, right? In your assignment 1, how did we represent dates? An ISO 8601 string, right? So it was a string representation. How does Unix represent a time? It represents it by one single integer number, representing the number of milliseconds since an epoch. The Unix epoch is January 1st, 1970. Right? In fact, I can tell you what time it is in Unix time right now. Time now. Right? Unix time now. There we go. If we can get it to load, unixtimenow.com. Right? Come on. All right, well, there we go. Right now it is 167.6652.709. Right? That's the time right now. If we go back to before 1970, January 1st, 1970, then we go into the negative numbers. Right? This does have a problem with the 2038 problem. Yeah, there we go. Read all about it on Wikipedia. That any Unix system that is using a 32-bit number to represent the number of milliseconds since 1970 is going to run out of time in 2038. Right? So we've got what? 15 years, right, to upgrade all these systems to 64-bit numbers, which will give us several trillion more years. But eventually, several trillion years in the future, we're still going to have to upgrade. Right? So that's another way of representing time. Another way is 3 integers, and that's exactly how it does it. An integer for the year, a short, which is a 2-byte integer for the month. Why? Because you only need to represent 1 through 31, or 1 through 12, excuse me. The day is also a short because 1 through 31. But did we have to worry about any of that when we designed this person class? Nope. Again, who cares? Now, you do have to care if you are designing the object. So if you're designing that weather data object, or if you're designing the customer object in your project, all right, then you have to care. But once you've designed it and you put it on the shelf, do you ever have to care about it again? No, you just use it. That's what abstraction is. Another example would, of course, be how Java represents a string. Does anybody know? Let's find out. Before I look, how do we represent strings in C? A char array with what has to be at the end, null terminating character. In other words, there's a lot of work to do that's put on you, right? Where is it here? Come on. All right, fine, I'll just byte. There we go. Byte. There it is. So it's not a character array. It's not a char array. There are chars in Java, but it's not a simple char. Why? Because chars are ASCII text. This is a byte. Why? Because in Java, you have Unicode support. You can represent CJK fonts, Chinese, Japanese, Korean fonts. You could represent Cyrillic. You could represent ancient hieroglyphics. You could represent the smiley emoji. Right? Why? Because it represents strings by bytes. Again, did you have to worry about that? No. That's what abstraction is. It's information hiding. How is this thing implemented? How is this data represented? I don't know. I don't care. I'm just going to use it to solve some problem. Right? The other pillar, the second pillar, is encapsulation. This one we have talked about explicitly. It's the grouping of data that acts together in one logical unit. It's the protection of that data using private keywords and maybe even final everywhere. Final, right? Why? Because you want to make sure that nobody changes this stuff. You should prefer immutable objects. Undo, 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 undo. There we go. So it compiles. And then finally, the grouping of methods that act on that data. It would be breaking encapsulation by locating data or methods that act on that data outside the class. When we originally started with this isotope demo, this decay function was some public static method somewhere, right? That was wrong. That was wrong from an object-oriented programming point of view. We then took that decay method and put it in the class where it belongs, right? It's just basic code organization. Just ask yourself, what is this thing doing? Oh, it's doing something with books. Where does it belong then? In the book class. What is this thing doing? It's doing something with the author stuff, their first name or the age of the author. Where does it belong then? In the author class. It doesn't belong here, right? Put your toys away where they belong, right? Author stuff goes in the author class. Book stuff goes in the book class. Bank stuff goes in the bank class, et cetera, right? Student stuff belongs in the student class. All you have to ask yourself is, what is this thing doing? What does it involve? And if the answer is, oh, it's student stuff, well, then your conclusion is it belongs in that class, right? Good abstraction and good encapsulation work together like MC Escher. So hopefully you've seen the MC Escher. You've probably seen it without knowing it was MC Escher. Let's pull it up. MC Escher hands painting. Right. Come on. There we go. Not hand, but there we go. That's the one I want. One hand drawing the other hand. The yin and the yang, if you want to call it, whatever. They're complementing each other, right? If you've got good abstraction, then you probably have good encapsulation, because you can't have good encapsulation with bad abstraction and vice versa, right? These two things kind of work together to draw on each other, right? Good abstraction and encapsulation work together to make code isolated, more easily testable, and you control side effects, or you limit the side effects, and reusable. Reusable because once you've created a person class, guess what? That person can be a customer. They could be an author. They could be an editor. They could be a reader, right? They could be anything, right? You could reuse that code over and over and over again. Anytime you need a representation of a person. Once you've got code that represents a date, you can use that over and over and over again. That's why they build it into the language, right? Once you've got a class that represents a string, all your C headache woes go away, because no null terminating character, no memory management, Unicode support instead of just ASCII text support, right? You don't have to worry about any of those details anymore. Right? More easily testable in that this thing is a person class, and it's isolated from the book class, it's isolated from the student class, it's isolated from anything, right? And now I can test it in isolation of everything else. Is this class good, right? Yes, then great, it passes all my tests. And that only comes from isolation. You can also control and limit side effects. Let's come back over here and break encapsulation, the second part of encapsulation, by making this public. Right? I am no longer protecting that data from the outside world. What can the outside world do now? They can set their first name to null. They could set it to UNL, right? That's nobody's first name. Maybe there is somebody named UNL out there, right? But we can control those kind of side effects, but only if it's private. Right? Always prefer private immutable objects. Okay. All right. That was our review and formalization of everything that we've covered up to this point in the last week and a half. Any questions on the first two pillars? Because we're about to get into the other two pillars. One of them is kind of trippy, right? That's polymorphism. Polymorphism is kind of trippy, except that you've probably seen it before, just didn't know that it was polymorphism. And inheritance, which is something that is new probably for everyone. No? Okay. So then what is inheritance? Inheritance allows you to reuse a class by extensing it, right? So I'm misspelling that there intentionally because extends is the key word in Java to define a subclass, and creating a subclass. So the way that you should look at it is we've got this superclass and this subclass. Another way that you can look at it is as a parent class or a child class. Just like in a a family tree, right? We've got ancestors up here and descendants down here. We've got a tree kind of structure here. Common functionality and state and behavior, what you can do is you can put that into the superclass so that everybody down here can share it. Except that when you get down here, you have some specific behaviors, right? So you can override and provide that specialization. You can override whatever is inherited from your parent. You inherit some from your parent and go, well, okay, that's great, but I don't want to do it that way. I want to do it a different way, right? Just like everybody does, right? They inherit certain genes from their parent and behaviors from their parents, but ultimately they do things their own way, right? So they inherit some, but they can always overridden how they do things. Classic example is going to be an animal, cat, and dog. What are the relationships between those three things? So a cat and dog, what are they both? They're an animal. They're animals. So therefore, a cat is an animal. A dog is an animal. So this already suggests a superclass, subclass kind of relationship, a parent-child relationship. Now I'll ask you, what are the relationships between a cat and a dog? Is a cat a dog? No. Is a dog a cat? No. That's called an invariance. We'll talk about that formally later on. But what about the other relationship? What about an animal versus a cat? What if I had a generic animal in my hand right now? Right? Just imagine it. Well, can you imagine just a generic animal? Is there such a thing? Is there animal? It doesn't make any sense, right? It has to be a little bit more concrete. That's what getting into abstraction. There's the abstract idea of an animal, and only when we get down to the nitty-gritty and, okay, this is a cat, this is a dog, right? They're both animals, but now I can actually imagine this dog in my hand here, right? But a dog is an animal, but is an animal necessarily a dog? No, it could be a cat, it could be a bird, it could be a human, right? It could be something completely different. So we've got this triangle of relationships, right? We've got a superclass and its subclass. Between them, these are not comparable. A cat is not a dog is not a cat. They're comparable to their parent. A cat is an animal, a dog is an animal. But are they comparable downwards? No, not necessarily. That's called an invariance, covariance and contravariance. Right? Again, we'll define those formally later on. What I want to do with the rest of our time here is to go through yet another demonstration, another exercise, to show you the power of inheritance. So what we're going to do is we're going to start a small little financial application here. We're going to support savings accounts and annuities. Well, what is a savings account? Everybody should have a good idea of what that is. You take a chunk of money, you throw it in the bank. That bank pays you interest on that balance monthly. So if I've got $100 in a savings account and it pays me, last year it would have been ridiculous, but this year 5% interest. Right? Everybody's paying 5% interest now because of inflation, right? So it's 5% interest. At the end of the year, I would have expected to have a little bit more than $5 paid out to me in interest, but it's going to be paid over month by month by month, okay? So at the end of the year, I'll have $105 and some change, okay? An annuity is a product whereby you purchase an annuity, like you pay them like $1,000 or something. And over the life of that annuity, they give you a monthly amount, right? They pay out $500 a month or something like that, right? And then at the end of that term, that's done, it's gone. The idea is that the amount that is paid out over time exceeds what you actually paid for the annuity, right? Hopefully. Financially, annuities almost never make sense, right? They're kind of scam products. Don't ever buy an annuity without reading the full details and understanding what it is, right? But that's what it is, right? So I've got these two different kind of financial products, right? Let's come over here to my demo, and I'm going to go ahead and get rid of all this stuff. Right? There we go. All right, so to do, I want a savings account with say $100 in it that pays 5% interest, APR. APR is short for annual percentage rate. And to do, I want, by the way, in your programs, do you leave to-dos in there? No, Cruft, you did it, right? It's not to do, you're done, right? So you're done. Get rid of it. I want an annuity that pays, say, I don't know, $500 per month for, I don't know, 10 years. Right? It doesn't matter how much I paid for it up front. Right? So one thing I want to emphasize here is I want a savings account. Right? I want a savings account. I want an annuity. I spelled annuity right? Or is it one N? What is it spelled like over here? It's two N's. You don't know how to spell annuity, Clips. All right. Anyway. So what's my first step? I see that a savings account has a balance, right? As we said over here. It has a balance and it pays an amount of interest. Right? So what should that be screaming out to you again? Make a class. So before I even get started on the functionality, let's start thinking about how we can design this class. New class, right? So tell me, what should I call this class if it represents a savings account? Savings account. Do what it says on the tin. Account, there we go. I'll leave it like that for a second. All right, get rid of book, get rid of isotope, get rid of person. Let's go back to demo. I want an annuity that pays $500 a month. So what should that be? It's got a monthly payment and it's got a number of years as a term. We call that a term, right? So what should I be doing? Creating a class called annuity. I thought annuity was this correct spelling. Annuity. Wow, everything is slow today. I don't care about the spelling anyway. Yeah, I did it right. Anyway. All right, so again, it's an inversion of your normal approach to programming. Programming, like when you start out in computer science, when you take a problem, you break it down into smaller and smaller parts until there's a function to do it, or you just write a for loop to do it, right? Here, I'm not even starting out with the functionality. I am starting out with the representation, the data representation. That's the important first step. So tell me, what is a savings account? Balance, I like that, right? And what type of variable should balance be? A double. Why? You can have $100.50, right? Now, in real financial applications, they skew doubles. Why? Because doubles still have a finite precision. So they use a library to do it, like a big decimal, right? That has arbitrary precision. Or they use integers, and then what they do is they map everything up. So that's not going to be a balance, it's a balance in cents, right? So they just simply multiply it by 100. That gets us into, over here, oh no, okay, there we go. That gets us into what? Yagni. Don't worry about that, right? In fact, what you could do is there is a currency class, Yagni, right? Don't do it. All right, so I've got a balance, double balance. That's good enough for now, right? And that's engineering. What's better than good? Good enough for now. Later on, when you have a very good reason to change this design, then do it. Right? Make it into a currency class. Make it into an integer, whatever. Right? But for now, double is okay. What else do we have? We have what? Interest, which is represented as an APR, double APR. Good question. What does APR stand for? Annual percentage rate, for those that know, right? For those that didn't know, would it have been easier to go annual percentage rate? Probably. And you're not paying by the character, so just write it out, right? This is arguably an okay variable name, or APR. That's probably an okay variable name in the context of a financial application. Because if you're in a financial application anyway, you probably know what an APR is, right? That's slightly better, more explicit. It's going to take you some more typing, but guess what? We've got auto-completion, right? It's the 21st century. You're not going to be typing this out every single time, okay? What else do you have? I want a savings account. So probably what? Owner, right? Owner, right? Who owns this savings account? Ah, person, right? Code reuse, right? This gets us back into why we do these things to begin with. Guess what? I don't have to worry about that, do I? Right? All right, great. Owner, anything else? We could go ahead and get fancy and have like an open date, right? Local date, right? Account, open date, whatever, right? I'm going to go ahead and leave it like this for now, okay? What else do you need for an object? What is an object again? It is identity, state, and behavior. I don't have yet behavior. That comes later. I have state, 3 different things, but what else do I need? Probably an identity. How would you identify a savings account? How does a bank identify a savings account? An account number, right? So that could be an integer, right? Account number. This is account number 12747, right? Or what's another way of representing that? Probably maybe a string. Why? Because this is account 1247-A3, right? You could have alphanumeric strings instead. Which one do we go with? String? I'll go with string for now. Do we know? Not until we read the document, or read the requirements, right? There's something called requirements elicitation, where you're going to design a system, right? Now, in the context of this course, we've already given you the requirements. That's the project overview handout. Pablo Myers has this farm mart stores, and here's his business model, and here's how it works, right? That kind of stuff you would have to actually suss out from the client. So you'd go to the client and you'd say, okay, well, your account numbers, give me an example here. Oh, a number, are they always going to be numbers, or are there going to be leading zeros like your NUIDs? Are there going to be letters? By the way, you're only using 5 digits. That means that you can have at most 10,000 accounts. Are you sure you want to do it that way, right? You go back and forth with the client. This is called requirements elicitation, right? And you're eliciting stuff out of a client that doesn't know what the hell they're doing, right? Because they wouldn't be hiring you to actually implement their system and design their system if they did know what they were doing, right? I can't tell you how many times I've seen insane business rules simply because they weren't really thinking of what they were doing, right? But once you have to put this down so a stupid computer understands it, then those design defects start manifesting themselves and it becomes obvious, right? I'm going to go ahead and go with string here. All right. Good encapsulation means that we're going to protect this data. So what should I do? Private final. Good. Okay. Now it's not going to compile because I don't have my constructor. I've now demonstrated this no less than 6 times, so I'm going to skip that because we only have about 5 minutes left. Let's go over here to annuity. I'll do it over the weekend, and when we come back to this demonstration on Monday, it'll be done. Right? Annuity. What is an annuity? What was it again? It pays you a monthly amount, right? So that's probably monthly payment, right? And that's going to be a currency, double, whatever you want. Again, double for now, right? Something else later, maybe. Monthly payment, monthly payment, there we go. What else? Certain number of years, right? So that's called a term, int years, term years. There we go. Now this is kind of you're getting close to something here called Polish notation, right? Because it's kind of stupid, right? There is a really, really old way of doing things, of putting the type of variable in the variable's name. Have you ever seen that before? No, it died a long time ago. Don't do things like that. However, years in the variable name is kind of close to that. It's telling you what that this is an integer and it represents years, not months, right? How many months would this be if it's in years? If it's 10 years, how many months is that? 120, right? If I wanted to represent this as months, I probably should put that into the variable name, right? Because it gives a hint as to what what this is doing. Just like the mass problem, is it kilograms, is it grams, right? Well, put it in the name and you're good to go, right? Until you have a very good reason to come back and have a duration. We could do that right away if we wanted to. I'm going to keep it simple. Int, term years, okay? What else should it have? I want an annuity. Right? So what should that be screaming out to you? Probably an owner, and while we're at it, probably an account number, because an annuity is an account, right? Okay. Private final, private final. Now, what's the final observation before we go into this weekend? Into this awesome weekend that sees NCAA baseball starting tonight at 8 o'clock, right? If anybody cares, right? So, what's our final observation here before we go into that weekend? Yeah, two classes, very, very similar to each other, that share the same thing. DRY, don't repeat yourself. What I'm going to do on a Monday is I'm going to take these two things and I'm going to elevate them up to a superclass, right? An asset or an account or something like that. Because every account that I define is going to have an account number and an owner. Don't repeat yourself. Create a hierarchy, right? So that all that repeated code is in one place, the superclass. And then everything down below it inherits that. That's what we're going to do on Monday.